Now that we've covered the basic definition, let's talk further with some facts about eigenvalues and eigenvectors. This first fact was covered in the practice from the previous video, and that is that only square matrices have eigenvectors. The easiest way to explore this is just to consider what would happen if we used a rectangular matrix A. If A is m by n, m not equal to n, of course, then the matrix X must be n by 1, which would make the resultant B m by 1. So here, X and B don't live in the same space, and it's impossible for B to be a scalar multiple of X. Eigenvectors and eigenvalues come in pairs. An n by n matrix has n eigenpairs, although some eigenvalues may be 0 if the matrix is not full rank. We'll talk more carefully about this third fact in a minute. Next, all square matrices have eigenvectors, but most of them will contain complex numbers. Recall, a complex number is one that involves the square root of -1, or I, the imaginary number. So if you just pick a random matrix and put it into R and ask for the eigenvectors, chances are it will come back with some complex numbers involved. The eigenvalues of a matrix are commonly called the spectrum of the matrix. So anytime you see things that involve spectral methods, spectral clustering, for example, I would be a good point person to ask for further information on those techniques, as they're, by their very nature, involving linear algebra. And this last fact is very important, and that's that any scalar multiple of an eigenvector of A is also an eigenvector of A with the same eigenvalue. Here I have that same example we did on the previous slide. The matrix A, and X is 1, 3, and we had determined that the corresponding eigenvalue was lambda equals 2. So I want you to pause the video and try and see what happens if I put the vectors V, U, or Z into the eigenvector equation. If I multiply A times V, what I should end up with is still 2 times V, because V is also an eigenvector of A associated with the same eigenvalue. Now, trying these 3 examples may convince you of this fact, but in general, this is a simple proof and one of the few that I will do in this class. If we have AX equals lambda x, which is to say, if X is an eigenvector of A with eigenvalue lambda, and C is some constant, then if I multiply A by C times X, that means if I take a scalar multiple of X and multiply it by A, well, since C is just a scalar constant, I can bring it outside of the parentheses, and of course, AX is equal to lambda x. And again, now lambda and C are both constants, and it does not matter in which way I multiply constants, so that would be the same as lambda times Cx. So looking at the very left and the very right, I can see here that Cx is also an eigenvector of A with the corresponding eigenvalue lambda. So this brings us to the idea of an eigenspace. For a given matrix, there are infinitely many eigenvectors associated with one eigenvalue, because any scalar multiple, positive or negative, can be used. So this collection of vectors is called the eigenspace associated with the eigenvalue. In our previous example, the eigenspace associated with lambda equals 2 is the span of 1, 3. Of course, I could also say it's the span of 2, 6. I can put any example in these brackets here. Well, geez, with this in mind, what should you expect from software? If the software can give you infinitely many answers, it should be a question of, well, what answer is it going to give you? You have a guess? That's right, it's going to give you the unit vector associated with that span. Now, here's the kicker. Is there only one unit vector associated with a span? No, there are two. And so everything you do that has to deal with eigenvalues and eigenvectors from software can give you different answers that are unique up to a sign, meaning that SAS may give you the positive version of that eigenvector, and if you go to R, maybe it will give you the negative version of that eigenvector. And that will be something that's important to be aware of, especially if you have people in a group that are using different softwares and replicating analyses. Now, as I promised, we're going to revisit that fact about 0 eigenvalues. And just consider, what would happen if lambda equals 0 is an eigenvalue for some matrix A? Well, it would mean that if I multiplied A times some vector, I would get 0. But recall, in the definition of eigenvector, x could not be 0. Well, so this means that some linear combination of the columns of that matrix A is equal to 0, which is the definition of linearly dependent. So the columns of A are linearly dependent, which means that A is not full rank, and you have some perfect multicollinearity in your data set. The next thing we'll want to be aware of is the ordering of eigenvalues. The eigenpairs, lambda I and vi, of a matrix are always ordered by the magnitude of the eigenvalue. And when we talk about magnitude, again, that's an absolute value. So the first eigenvector, v1, is the eigenvector associated with the largest eigenvalue in absolute value. The one final fact I'd like to share with you in this video is that symmetric matrices, like the covariance, the correlation, distance, similarity matrices, have several nice properties. The first is that their eigenvalues and eigenvectors are real, as opposed to complex. The second is that their eigenvectors are all mutually orthogonal. So if you normalize the eigenvectors to unit length, they will form an orthogonal matrix, or an orthonormal basis. And that's exactly what we're going to take advantage of in principal components. Let's get some practice with these facts, and then we'll start introducing principal components in a little bit more detail.